Alrighty, it's 12:30, so let's begin. I've prepared two problems for you guys today because there are really kind of two different ways that we can be asked questions about Thevenin and Norton equivalent circuits. The first problem that I have prepared is one in which we're trying to find the Thevenin equivalent circuit with respect to a particular resistor. So does anybody recall from the lecture video how I should approach a problem where I'm trying to find it with respect to a particular circuit element? What's the first thing I have to do? Nobody? All right. Well, the first thing I have to do is actually take that 10 ohm resistor out. That 10 ohm resistor is playing the role of a load resistance. So, and is actually this guy right here. And so we're just going to replace the 10 ohm resistor for now with an open circuit. And any time that you're asked to find the Thevenin equivalent or Norton equivalent with respect to a particular resistor, capacitor, inductor, electrical component effectively, this is the first thing that you need to do. You need to take it out of the circuit. So since we're trying to find the Thevenin equivalent circuit, that means that we're going to be interested in two pieces of information: the Thevenin voltage and the Thevenin resistance. So I'm going to define the Thevenin voltage with positive polarity terminal on the left. By definition from Thevenin's theorem, it is the open circuit voltage across the terminals where the component of interest was. So my question to you guys is then, how can I solve for this particular voltage, V Thevenin? Anybody have any ideas?
Can we change the power source to the same sources?
So could we do a source transformation on the practical current source on the right-hand side? Sure. So let's explore that. So I have a 5 amp source direction down, which means I'm going to have positive polarity terminal on bottom, negative polarity terminal on top. 5 times 40 is 200 volts, right? And then my 40 ohm resistor is going to be moved up to here. Okay. So what could I do next? Combine the voltage sources. So they're not in series, so I don't see how I could do that. So let's talk about what this Stavan voltage means here. And so I'm going to not necessarily do nodal analysis, but I'm just going to choose a reference node real quick to explain effectively what's going on. All right. And actually I don't even need to do that. I could have done it with Kirchhoff's voltage law, but anyway. One way to think about this Thevenin voltage is it's the voltage drop between this node, let's just call it VA, and this node VB over here. Okay, so VA minus VB would be equal to V Thevenin if we chose to do nodal analysis. We could alternatively, and this will really kind of give us the exact same relationship if you think about it. Let's call this voltage right here V50. If we wrote a Kirchhoff's voltage law equation around this loop, we could see that 8 volts is equal to VTH plus V50, which means that VTH would be equal to 8 volts minus V50. That's literally the exact same thing, it's just expressed in a slightly different way. That being said, we can find V50 as it's labeled in the circuit right now, using, in my opinion, a much easier method than nodal analysis. Anybody have any idea what that might be? So let me ask a slightly different question. We're looking at this 200 volt source on the right hand side. It's in, dang it, that's not the color I wanted. It's in series with this 40 ohm resistor, right? Which is in series with this 20 ohm resistor, which is in turn in series with this 50 ohm resistor. And then we're back down to the bottom node. So I have a voltage source in series with several resistors. So what method should I use to solve for the voltage drop over one of those resistors? Voltage division, there we go. So we can see pretty easily that V50 is going to be negative 200 volts, and it's negative. Let me explain why here real quick while I erase these things. So using our voltage division principles with the positive polarity on bottom, we should see the voltage drop over the 50 ohm resistor with this polarity, then the voltage drop over the 20 ohm with this polarity, and the voltage over the 40 ohm with this polarity. V50, I've defined it in the opposite, with the opposite polarity. We could just as easily change it, but I'm lazy and I'm not going to. So with that in mind, that's where we have that negative sign there. And so we should see that V50 is negative 200 volts times 50 ohms, the resistance we're interested in our numerator, divided by the total series resistance seen by the 200 volt source, which is 50 plus 20 plus 40. So this is going to be negative 200 times 50 over 50 plus 20 plus 40 is negative 1,000 over 11, or negative 90.909 volts. So from this, what's our Thevenin voltage? VTH is 8 minus negative 90, or 8 plus positive 90, etc. So 98.909 volts. So the method that we've used here, where we did a source transformation and then voltage division and then KVL, I guess, to find our Thevenin voltage, isn't going to work for every circuit. What's great about the Thevenin and Norton equivalent circuits is that it really doesn't matter what circuit analysis technique you use to find, say, the open circuit voltage, which is the Thevenin voltage, the short circuit current, which is the Norton current. It is very important about how we go about determining the Thevenin resistance, which is actually what we're going to do next. So to determine the Thevenin resistance, we're going to start with this exact same, our original circuit, with the 10 ohm resistor taken out. So let's see. Here's our 8 volt. Here's where our 10 ohm resistor was. Here's a 50 ohm resistor. Here's a 20. Here's a 40. And here is our current source, 5 amps direction down. So to determine the Thevenin resistance, Thevenin's theorem tells us that we need to be looking at a dead network. What a dead network is a network where all of the independent current and voltage sources have been turned off. We always have to leave the dependent sources on, but in this case, there won't be any dependent sources, and we won't actually start working Thevenin and Norton circuits with dependent sources until next Wednesday. So how do I turn a voltage source off? So for a voltage source to be off, we want the voltage to be 0 and any amount of current that needs to flow through it can. If we replace, yeah, so it'll be a short circuit. And how do we turn off a current source? That's the open circuit, which is the same as me just plucking it out. So we're going to look in through these terminals of our dead network and determine our Thevenin, which is just the equivalent resistance that we see. So what's that going to be in this case? So we're about to hit exam 1, and if you guys can't do resistor combinations, you're in poor shape.
It's the 50 ohm in parallel with the 20 and 40 in series, correct?
That is correct. So 50 in parallel with 60. So we'll have 50 ohms times 20 ohms plus 40 ohms divided by 50 ohms plus 20 plus 40. 50 times 60 divided by 50 plus 60. 300 over 11, or 27.273 ohms. So this big circuit that we have here up at the top is electrically equivalent to 98.9. This. So we've taken this guy here and we've converted it down into a simple practical voltage source connected to our load resistor of 10 ohms. This is a Thevenin equivalent circuit. It's just a practical voltage source representation of our original circuit. Okay. So to be clear, the Thevenin equivalent circuit contains two parts. The Thevenin voltage, which is just the open circuit voltage where the resistor or component of interest was, and the Thevenin resistance, which is determined by finding the equivalent resistance as seen from where our component of interest was while looking at a dead network. And it is critically important that you turn off all of the voltage sources and current sources and stuff like that. So any questions on this example problem? Hopefully fairly straightforward. Alrighty, so the next problem that we have, we're going to determine the Norton equivalent circuit seen between terminals A and B of this guy. And since we're looking for the equivalent circuit with respect to a set of terminals, we don't actually have to take anything out of the circuit whatsoever. So we can leave it as is and work from there. So let's first define what the Norton current is, much like we defined what the Thevenin voltage was. The Norton current is the current that flows, or that would flow, if we short-circuited our terminals A and B. I'm arbitrarily choosing the direction down right here, just like I arbitrarily chose positive polarity terminal on the left-hand side for the Thevenin voltage above. So the Thevenin voltage, again, is the open circuit voltage. The Norton current is the short circuit current, which means we short circuit our terminals or short circuit our component of interest if we had a component in there, and then just measure the current that flows through the short. So how are we going to figure out that current? Any suggestions? I'm sorry, could you speak up, please? That is correct. That is 12 kiloohms. So the 8-volt source is not in series with the 12 kiloohm resistor or the 7 kiloohm resistor. So a source transformation isn't going to work here. The 12 milliamp source isn't in parallel with the 12K, the 3K, or anything like that either. So source transformations are off the table because we don't have any practical source. So we could do nodal analysis, but nodal analysis gives us the unknown voltages in the circuit, and we're looking for a current. So why don't we do mesh, right? We're trying to find a current. Let's just use mesh. So let's call this guy right here mesh current 1. This guy mesh current 2. And I'm about to do something that might not be obvious to you guys, but I'll explain it. I'm going to call this guy mesh current 3. The reason I'm going around the 8 kiloohm resistor is because it's in parallel with a short circuit, and so I know that no current will flow through it. It may as well not even be there. I could have included a 4th mesh current where I would have had to make another equation that says I3 minus I4 is equal to 0, because I know no current's flowing through the 8 kiloohm resistors, which is just saying I3 is equal to I4. So I'm just cutting out that extra couple of equations to get to the exact same point. No current flowing through the 8K because it's shorted out. So everybody clear on my methodology here. All right, so we got 3 currents, 3 unknowns. Because we have a current source on the inside of the circuit, that means we're going to have to employ the super mesh technique. So I'm going to go ahead and write down that path in, let's say, just for the sake of argument. So I want the smallest path that encloses it. So that's going to be this guy. All right, so I'm going to start with my current relationship. Sure. So anytime I have a current source on the interior of the circuit, like this guy, so it's not on the perimeter where I could say simply that, you know, I1 was equal to 12 milliamps or something like that. So anytime I have a current source on the inside of the circuit, I have to write a super mesh around. The reason for that is if I tried to do a Kirchhoff's voltage law loop equation around just I1 by itself, I would have to account for the voltage drop over a current source. And the voltage drop over a current source is not related in any way, shape, or form to the current flowing through the current source. So I would just have an unknown quantity in there. When I write my mesh equation for I3, I would have that exact same voltage, but with the opposite polarity, essentially. And so they're just going to wind up canceling each other out. So it's just like the super node technique, but now we're avoiding dealing with current sources as opposed to voltage sources. All right, so our current relationship equation is going to be what? How do we express the current flowing through our 12 milliamp source in terms of our mesh currents? I3 minus I1, that's it. All right, now let's do our super mesh. So this is KVL at super mesh 1, 3. Let's start from here and follow the purple path around. So what do we see? Positive 8 volts because we see the positive polarity terminal first. All right. What's next? The 3 kilo ohm resistor, absolutely right. So there's a whole bunch of wire between the negative polarity terminal of the 8-volt source and the 3 kilo ohm resistor, but all of that is effectively a short circuit, so there's no voltage drop over it. So the next thing we see is this 3 kilo ohm resistor. What's the current flowing up through the 3 kilo ohm resistor? What's the total current flowing up through the 3 kilo ohm resistor would be a better question.
I3 minus I2.
I3 minus I2, thank you. And what's the next thing we see? The 12 kilo ohm resistor, alrighty. And what's the total current flowing from right to left through the 12 kilo ohm resistor? That is correct, I1 minus I2. And we have ended where we started, so we're good to go there. Our last equation is going to be a KVL equation at the regular mesh 2. So starting from the bottom left-hand corner, what are we going to have? 7 kilo ohms times I2. Alrighty, what's next? 12 kilo ohms. What's the total current flowing from left to right through that 12 kilo ohm resistor? I2 minus I1. Alrighty, and what do we see last? All right, and what's the total current flowing down through the 3 kilo ohm resistor? All right, so we have 3 equations, 3 unknowns, so we should be able to solve for them. So let's do that up. All right, so my first equation, the coefficient for I1 is -1. My first equation, the coefficient for I2 is 0. And the coefficient for I3 is +1. And it's equal to 0.012 amps. In my second equation, my coefficient for I1 is 12,000. My coefficient for I2 is -3,000 plus -12,000, so -15,000. And my coefficient for I3 is 3,000. My constant term, when I move it to the right-hand side of the equal sign, is negative. And in my third equation, I have -12,000 I1. 7 plus 12 is 19 plus 3 is 22,000 I2. 19 plus 3, yeah, 22,000 I2. My coefficient for I3 is -3,000, and my constant term is 0. I get -4.076 milliamps, -1.143 milliamps, and 7.924 milliamps. Anybody else get similar results? Always a chance I type something in wrong, so why not? Anybody here to refute my answers? I'm getting a thumbs up, so let's assume that I'm correct here. If not, the methodology is correct. I just typed something dumb into my calculator. So, all right. So now that we know what those 3 mesh currents are, what's I Norton? I3. 7.924 milliamps. There we go. Alrighty, so to determine the Thevenin equivalent resistance, we're going to do the exact same thing we did previously. So we're going to have our circuit, but we're going to turn off our voltage sources and turn off our current source. So our voltage source turned off looks like a short circuit. Our current source turned off looks like an open circuit here. Then we're going to have 12 kilo ohms. Three kilo ohms, 7 kilo ohms, eight. Here's our terminal A. Here's our terminal B. So we're trying to find the equivalent resistance, which you could call R Norton or R Thevenin. So Norton's theorem is effectively the source transformation of Thevenin's theorem. So the Thevenin voltage, excuse me, the Thevenin resistance and the Norton resistance are literally representative of the exact same quantity, and they're found in the exact same way by looking at a dead electrical network and measuring the equivalent resistance seen between the terminals. So I'm going to call this R Thevenin. So what's our equivalent resistance going to be, or how can we find it? So let's identify our nodes real quick. All this guy is node A. All this guy is node B. And then we got that one other node right here. So to me, this looks like, let me change my size of my thing here. The 8 kilo ohm resistor is in parallel with the 3 kilo ohm resistor, is in parallel with the series combination of 12 kilo ohms and 7 kilo ohms. Can everybody understand how I came to that, right? So between A and B, I have the 8K, or between red and blue, I have the 8K and the 3K, and then also the 12 in series with 7. So I do this to the -1 power, and I find that one over 3K plus 1 over 12 plus 7 is 19. .957 kilo ohms is what I got. Hopefully you guys got something similar. And from this, our Norton equivalent circuit. Yes.
You have the 7 kilo ohm and the 3 kilo ohm switched?
Maybe I do. Let's check. I absolutely do. Thank you. So I got these guys backwards when I redrew my circuit. Thank you very much for pointing that out. So let me, 7 on the left, 3 on the right, which means 7 goes here, 3 goes here. So that's going to change something. Thank you very much for pointing that out. Let's try this again. 1 over 8 plus 1 over 7 plus 1 over 15 to the -1 power is 2.989 kilo. So we're going to have as our equivalent circuit, excuse me, a 7.924 milliamp source in parallel with a 2.989 kilo ohm resistor. And so we've made this big ugly circuit look like this simple electrical equivalent practical current source. That's the beauty of Thevenin and Norton equivalent circuits. For any two-terminal network, meaning that it just has an open circuit that we can deal with somewhere, whether that's taking it out, taking a component out to find it with respect to a particular resistance, or finding it within a set of terminals, regardless of how complicated it is, as long as it's a linear network, which we covered way back in lecture 5, we can simplify it down to a practical voltage source representation using Thevenin's theorem, or a practical current source representation using Norton's theorem. Very, very powerful tool for power analysis, particularly. Like for instance, if we were designing one of the power supplies or oscilloscopes or something like that in back, we wouldn't go through and nitpick every single thing to find out whether or not we were going to blow a fuse out. We'd look at the Thevenin equivalent and then find, okay, what's the power that's going to be delivered here? Is it too much for this component or not? We wouldn't go through on a component by component level. We'd look at subsystems, find their Thevenin equivalent, and just use that, because it would be a nightmare to analyze that whole thing in one go. Alrighty, so there's 20 minutes remaining, so if anybody has any questions about the in-class assignment stuff, now's the time for it. For you guys that are here in person, try to work with a partner or whatever and figure things out, and if you can't figure anything out, let me know, and I'll come out and help you. Today we're going to be talking about Thevenin and Norton equivalent circuits. I have 2 examples prepared. The first of which is finding the Thevenin equivalent circuit with respect to a particular component, okay? Whenever we're trying to find the Thevenin equivalent with respect to a component, we always have to remove that component from our circuit in order to perform our analysis. So with the 10 ohm resistor removed, the circuit that we are looking at is this guy. And our ultimate goal, at least for this step, is to determine the Thevenin or open circuit voltage across the terminals where we removed our element of interest, okay? I'm arbitrarily choosing the left polarity terminal, the positive polarity terminal on the left. On your exams and stuff like that, I explicitly specify, and you won't see this until exam 2, but I explicitly specify positive polarity terminal on the left, right, up, down, to center. All right, so our goal, again, is to find that open circuit voltage, or the voltage drop between this point in the circuit and this point in the circuit. So, does anyone have any suggestions on how we may accomplish this feat? All right, so do a source transformation. All righty. So 5 amp down means that the positive polarity terminal is going to be on bottom, negative polarity terminals on top. 5 amps times 40 ohms is 200 volts. And our 40 ohm resistor is now placed in series. Alrighty. So what can we do next? Okay, so it depends on which resistor specifically you want to do, and depending on how you want to approach this, it might be a step that it does simplify the circuit, but not enough to actually make a difference. So let me explain what I mean by that. All right, so we can look at this Thevenin voltage in a couple of different ways. One way that we could look at it is if we were doing nodal analysis. Let's call this guy node A, this guy node B, and then if we combine those resistors, we'd get rid of that node in the middle, etc. We could call this guy node C. So our Thevenin voltage would simply be the difference of VA and VB, right? Now, let's look at it in a slightly different way. It's actually going to give us the exact same result as that, but we're not going to have to set up a system of equations to figure things out. So what I'm going to do is I'm going to assign a voltage drop over the 50 ohm resistor like so. If we wrote a Kirchhoff's voltage law equation, we could see that 8 volts is equal to our Thevenin voltage plus that quantity V50, which means V Thevenin is simply 8 volts minus that voltage V50. The exact same relationship we got a moment ago using nodal analysis, but expressed in a slightly different way. Now, the reason why I prefer this method is because we can actually figure out what that voltage V50 is pretty easily. And so let me explain myself. The 40 ohm resistor and the 200 volt source are connected in series, right? The 20 ohm resistor and the 40 ohm resistor are also connected in series, correct? And lastly, the 20 ohm resistor and the 50 ohm resistor are connected in series. And then we're back down to the bottom or bottom node of our voltage source. So from the perspective of that 200 volt source, it just sees 3 resistors in series. And we're looking for the voltage drop over one of those resistors. So how could we find that voltage in the most efficient method? Voltage division, exactly right. So our voltage V50 is going to be negative 200 volts. And the reason it's negative, let's explain that just real quick. I think I've done it multiple times at this point, but I still see mistakes. We would expect, based on the polarity of our 200 volt source, to see the voltage drops over our resistors with these polarities, right? The voltage rise given by our source is the sum of the voltage drops by the resistors connected in series to it. Well, the expected polarity for the voltage drop over the 50 ohm resistor is exactly opposite as how I've defined the voltage V50. So that's where this negative sign comes in. So I just want to be very clear about that. Then we're going to have in our numerator the resistor we want, which is the 50 ohm resistor, and in our denominator, the total series resistance connected to our voltage source, 50 plus 20 plus 40, and this gives us plus 20 plus 40. Negative 90.909 volts. So from this, our Thevenin voltage is 8 minus negative 90.909 is simply 98.909 volts. So any questions about how we found the Thevenin voltage here? Now in this particular circuit, we did a source transformation on the suggestion of Mr. Carrick over there. And then we wound up using voltage division and then Kirchhoff's voltage law in order to find our Thevenin voltage. That's not going to work for every circuit. One of the beautiful things about Thevenin and Norton circuit analysis is that to determine the Thevenin voltage and the Norton current, we can really use whatever circuit analysis technique we are most comfortable with, as long as we understand what the definition of the Thevenin voltage and the Norton current are. So in this case, we kind of threw a couple of different things at it, worked out pretty straightforward. We could have started with our original circuit and done nodal analysis, and that would have been okay as well. There's only two unknown nodal voltages the way that this is drawn. Just whatever floats your boat works as long as you get to the correct answer. All right, so the Thevenin equivalent circuit is formed with the Thevenin voltage in series with a Thevenin equivalent resistance. And so the Thevenin equivalent resistance, we're going to start with the exact same circuit that we had at the beginning with the 10 ohm resistor removed. And then I'll talk about it for a moment. All right, so the Thevenin equivalent resistance, by definition, is found by looking into the terminals where we pulled our component out from, but we also have to be looking into a dead network. What a dead network means is that our independent voltage and current sources are turned off. Our dependent ones are always left off, okay? So how do I turn off the 8-volt source? Short circuit. How do I turn off the 5-amp source? Open circuit. So I'm looking in and trying to find the equivalent resistance. So what do I see? So you're saying they're all in series. If we identify our nodes, okay, that is correct. So we would see 50 in parallel with a series combination of 20 and 40. Is everybody okay with that? All right. So that's 50 times 60 over 50 plus 60, which is 27.272 or 273, that's 272 ohms. And so what this enables us to do effectively is we have done sufficient analysis that from the perspective of the 10 ohm resistor, what it sees so here's our 10 ohm resistor out here, is this practical voltage source, which has the Thevenin voltage in series with the Thevenin resistance. Okay. So we took this whole network, everything but the 10 ohm resistor, and simplified it down to those two elements. So it's doing very similar to what we did with our source transformation technique, except that we are not required to be able to do source transformation on anything. So if we looked at this circuit, you know, we did do a source transformation on the right-hand side, but we would have ran out of ways to do source transformations pretty quickly and not gotten to that Thevenin equivalent circuit. And so that's another useful tool there. So the Thevenin equivalent circuit and the Norton equivalent circuit, which we'll deal with next, are widely used in power analysis because the Thevenin equivalent is what's called the electrical equivalent of this larger network. So for instance, if I was trying to design a cell phone and I wanted to check out the power requirements of a particular subsystem, I wouldn't want to analyze that whole big ugly thing, which may include, you know, microprocessors, this, that, and the other. I only need to look at the open circuit voltage and or the short circuit current and or the Stavan Resistance to be able to know exactly how much power that particular subsystem is going to be able to dissipate for a particular load. So it's a shorthand method that we use in practical electrical engineering to save ourselves a lot of trouble of analyzing big ugly circuits when we can simply hook up a voltmeter and a multimeter and figure out how it's going to behave from two figures of interest. All right, and that's actually the lab we're going to do next Wednesday afternoon. All right, so any questions regarding the Thevenin equivalent circuit or the analysis that we did here? Anybody got anything? All right, hopefully it's fairly straightforward. I felt it was, but never know. All right, our next circuit, maybe a little bit more ungainly. We are asked to determine the Norton equivalent circuit. So the Thevenin equivalent circuit was a practical voltage source representation. The Norton equivalent circuit is a practical current source representation of a network. We're asked to find the Norton equivalent circuit seen between terminals A and B. So this is a very important distinction. In the previous problem, we were asked to find the Thevenin equivalent with respect to a particular component. That's why we had to take a component out. In this case, we're looking for it with respect to a pair of terminals, so we don't need to take anything out of the circuit at all right? So I want to be really clear about that. The Norton current is defined as the short circuit current, which means we have to place a short between our terminals and then measure the current that flows through that short. That's short circuit current by definition. So if in the previous example we were trying to find the Norton current, we would have shorted out the 10 ohm resistor and then work from there. All right, so my question to you all then now is, how are we going to find that short circuit current? What circuit analysis technique or combination of techniques might we use? Okay, somebody else, either in Zoom or here in the classroom, just throw something at the wall and we'll see if it sticks. Mesh analysis, that's absolutely what I would have chosen, okay? There are no practical voltage sources or practical current sources that we could do source transformation or anything on. We're trying to find the current, so mesh analysis seems like a pretty reasonable way to do that. So let's call this guy here mesh current 1. This guy down here, mesh current 2. And I'm about to do something that might seem a little bit odd, but I'll explain it in just a moment. This guy around the outside here, mesh current 3. So I'm purposefully choosing to effectively ignore the 8 kilo ohm resistor there. And the reason I'm doing that is because it's shorted out by the short circuit on the right-hand side. So it's the 8 kilo ohm resistor is directly in parallel with the short circuit, which means we know no current will flow through the 8 kilo ohm resistor. So I could have done something like this. Let's call this I3 and I4, and I would have had a fourth equation, but I know that I3 minus I4 is equal to 0, which means I3 and I4 represent the exact same thing. This is a waste of adding a couple of extra steps to an equation we didn't need. So using my understanding of how a short circuit behaves, I'm bypassing that 8 kilo ohm resistor. Alrighty, so we're doing mesh analysis. There is an interior current source, right? That 12 milliamp current source isn't on the perimeter of the circuit, it's on the inside. So that means we're going to have to apply a super mesh technique. So I'm going to go ahead real quick and identify that path. It's the smallest possible path that encloses the current source. So that's the smallest one that we can draw that encloses it. And now we'll start on our mesh analysis. So the first thing that I like to do is my current relationship equation. So how can I express the current flowing through the 12 milliamp source in terms of our mesh current? You say it. I3 minus I1. Alrighty, so we only have one current source, so we're only going to have one current relationship equation. Next, let's do Kirchhoff's voltage law around our super mesh. And let's see, it's between mesh 1 and mesh 3, so I'm going to be really original and label it super mesh 1, 3. And I'm going to start at the bottom left-hand corner, which I've circled, and just follow that pink path around. So somebody tell me what the first thing I see is. 8 volts. And it's positive because the positive polarity terminal is what we encounter first. What's next? So I hear two people kind of whispering. Yes, the 3 kilo ohm resistor. Yeah. I3 minus I2. So let's talk about this just real quick because it might be a little bit confusing. So there's a whole lot of distance between this node and this guy down here where we see the 3 kilo ohm resistor, but that's all just connected by a wire, right? So there aren't any resistors or sources or anything in that path. So that's why we're not adding anything else. We know the voltage drop over a wire should be 0. So it would just be adding 0 a whole bunch of times. So we see the 3 kilo ohm resistor. We're looking at it direction with the current flowing up. So the total current flowing up is I3, which is in the up direction as it passes through that resistor, minus I2, which is in the down direction. All right, so what's the last thing we see along that pink path? The 12 kilo ohm resistor, all righty. And what's the total current flowing from right to left through the 12K resistor? Yes, that's correct. I1 minus I2. We ended where we started, so we're good to go there. Our last equation comes from applying Kirchhoff's voltage law at our non-super mesh. So this is mesh 2. So we're going to start at the bottom left-hand corner and just follow I2 around that little path. So what do we have? Seven kilo ohms times I2, alrighty. What's next? Thank you, ma'am. And what's next? I2 minus I2. Alrighty, set that equals 0. Okay, so we have 3 equations, 3 unknowns. So we can solve for I1, I2, and I3. We'll take a moment to do just that. And quick enough on the draw with our calculator to have solved this system of equations yet? Alright. So, just heads up on the exam on Monday. There's going to be questions involving nodal and mesh analysis that will require you to set up and solve the system of equations using your calculator. So, you better be good at it. So, the format will be extraordinarily similar to the practice exams that have been available since literally the first day of class. Probably, but I'm too lazy to go find it. So, yeah. Yes, sir. Absolutely. Negative 4.076 milliamps. What did you get for I2, sir? Negative 1.143 milliamps, and lastly 7 point something. I don't remember. 924 milliamps. Great. All right. So now that we know those three mesh currents, what's I Norton? I3. Okay. Oh, excuse me. All right. So the next thing that we need to find is what's called the Norton equivalent resistance. The Norton equivalent resistance is literally the exact same thing as the Thevenin equivalent resistance. They represent the same quantity. They are determined in literally the exact same way. So to that end, we're going to have, let's see, we turn off our voltage source by replacing it with a short circuit. That's the guy on the left. I've turned off my current source by replacing it with an open circuit. And I have here's our 8 kilo ohm resistor. Here's our terminal A. We have a resistor down here, a resistor here, and a resistor here. And I'm going to refer back so I don't screw it up like I did with the earlier group. 12, 7 on the left, 3 on the right. We are looking in through this set of terminals and trying to find the Stavan resistance. So, what is it going to be? Anybody have any ideas? or how we might go about finding it. How are things connected, that kind of stuff. Okay, so the 3 and the 12 kilo ohm resistors are in series, so they look like a single 15 kilo ohm resistor. These terminals where the current source was aren't really doing anything, so I'm just going to erase them. Just wanted you guys to know where I took it out from. So what do we have now? Everything's in parallel. .989 kilo ohm. So this whole big circuit up here, we could replace with this. All right. That's all really that I've got prepared. So please take the next 20 to 25 minutes or so. If you have any questions about the in-class assignment, I'd be happy to answer them. Work among your peers and all that kind of stuff like you've been doing for the last couple of days to kind of try to figure things out. And when you get stumped, let me know and I'll come help.